Hi, today I'm going to show you why speeding up slows you down in orbit. We know that the gravitational force drops off with the distance squared, and the centripetal acceleration is inversely proportional to the distance. When we put these two equations together, we get a very strange result, that as the radius of our orbit increases, our velocity must go down. But then how do we get from this really fast inner orbit to this outer, much slower one? The energy is a really helpful tool to figure out what's going on in this situation. We know that energy is conserved, and that allows us to fix the total energy quantity. So you have the kinetic energy plus the potential energy. The kinetic energy is the same in all situations, mv square over 2. But the potential energy for these large scales is defined to be negative with an inversely proportional to the distance. As the radius increases and gets really, really large, infinitely large, the potential energy will drop to zero. And as you fall towards the sun, you would have given up gravitational potential energy, therefore the negative sign. And you're giving up gravitational potential energy, but gaining something in return. So the sun would have sped you up. So we can see, if we substitute velocity from our previous equation, that for a circular orbit, the total energy is also negative, and half of that of the potential energy. Here I have two circular orbits, the purple satellite and the green satellite. The purple satellite is much closer to the center and is much faster. So it has a greater kinetic energy than this green satellite. The green satellite is much farther away and has more gravitational potential energy. In this case, because the quantities are negative, that works out to having less negative gravitational potential energy as compared to the purple satellite. The total energy, also being negative, you can see has increased for the green satellite. So we see that as you increase the radius, the total energy must go up. But then how do you get from this configuration to this configuration of energy? So we have to use an intermediate, an ellipse. When we are really close in an elliptical orbit, our gravitational potential energy is the same as that of the purple satellite, as we are the same distance away from the sun. But our kinetic energy, as you can see, is higher, much too high to be bound by the force of gravitation. So our orbit extends more over the purple orbit and takes us farther from the sun. As we get farther and farther from the sun, we trade our kinetic energy for gravitational potential energy. But as you can see, the total energy, this small bar here, doesn't change in length. As we get to the exact farthest point from the center, we see that the gravitational potential energy is the same of that of the green orbit. Our total energy is lower though, because our kinetic energy is not high enough at this new radius to be enough for a stable circular orbit here. So it seems that as we crossed from this low point to this high point, first our kinetic energy was too high, and then it became too low. At some point in the middle, there must have been a balance, where the kinetic energy would exactly match the force of gravitation, and that would allow us somewhere here, so that the kinetic energy is the positive of the total energy and twice and negative of the gravitational potential energy. But at this point, this direction of our velocity isn't really aligned with a circular orbit. As you can see, the tangential here would be away. And so we are not able to form the circular orbit there. But we can use the ellipse nonetheless to get from this purple orbit to this green orbit. Here, our orange satellite is at a constant distance from the sun. And say we want to get to this red orbit farther away. This is the first phase of the Hoffman transfer. And we would achieve it in this manner. Now, watch carefully at the kinetic energy as I increase the speed. As the kinetic energy is increasing, the total energy is also increasing, but we haven't gone farther away from the center. So our gravitational potential energy is still the same. We're still at this position here. As our kinetic energy is increasing, our total energy is also increasing with it. And you can see that our velocity here is getting faster and faster, while the velocity at the farthest approach is getting lower and lower. So now we have stopped firing our rockets or something. Our kinetic energy is really high. Our total energy is much more than what it was before. Our gravitational potential energy has not yet changed. But as we go around, our kinetic energy will be traded with gravitational potential energy. And as we hit this mark, we are much too slow for to be in a stable circular orbit here. So we do this once more. Now we are at this position. We have the same energies as we achieved last time. And we are here with a much slower velocity. And we are destined to fall down again, speeding up as we go, losing gravitational potential energy as we come closer. And this orange bar decreases in length. So we will become fast once more. But we can stop this by increasing the velocity. As I increase my velocity, the length of this purple bar will increase. As you can see, the kinetic energy is rising. The total energy is also rising. The gravitational potential energy is not changing, as you can see, because this orange length is not changing. We are here and we're firing our boosters in that direction, which means we're being pushed downwards. As we increase our velocity, our kinetic energy increases, our total energy increases, and we hit a balance point again. Right now, our kinetic energy is positive. Our gravitational potential energy is twice of that and negative. And our total energy is half of that and negative. We have achieved a balance for a circular orbit again. And that's how you go from a small orbit to a large orbit. Thank you.